Hello everyone. So, in the last week, you've learned about the X-ray and the characterization techniques which are related to the X-ray, which uses the X-ray basically. So, we so I'll be giving a brief overview on the X-ray diffraction. So first, I'm going to talk about what is X-ray first of all, and the radiation and its interaction. How the X-ray actually behave upon colliding on the sample, or what are the mechanisms of interaction with the material. So I'm going to talk about that, and then the what is diffraction particularly, and the basic principles of XRD instrumentation and the analysis of the XRD data and its applications. So, as you know that the electromagnetic spectrum is a broad range, and in that we have the X-rays falling in between the gamma rays and the visible UV visible range. However, the X-rays are not typically found in nature, but these are generated uh, by a combined by a different mechanism using a cathode and anode, which I'm going to talk about. So these are artificial rays, but however the gamma rays and UV visible, these are all present in nature. So this X-ray also falls into some of the hard X-ray part falls into gamma ray region, and so this is the typical region where the wavelength is from 10 nanometers to 100 picometers. So coming to what is X-ray, so it is a electromagnetic radiation. So as I've told, the wavelength is from 10 picometers to 10 nanometers, and you can convert it into frequency and energies in electron volt. So these are produced by using a very high speed electrons on a heavy metal target. So the electrons, this is basically a anode and cathode system. So where we have a source of electron, which is the tungsten filament, which acts and a very high voltage between the cathode, that is the tungsten. Tungsten is the cathode basically, and that is the source of electron. And a very high voltage is applied. So to generate the X-rays, we have a cathode and anode and a metal target. So cathode here is the tungsten filament, and which is the source of the electron. And a very high accelerating voltage is applied between the anode and cathode to actually produce the uh, electron X-ray. Uh, so the anode is a tungsten rhenium target on a molybdenum core, and that is backed with a graphite or water-cooled block of copper containing desired target. So here you can see the copper is there, and this is containing a target, and the electrons are falling on this target from and passing through the beryllium window. So this is transparent to the X-ray. That's why we use the beryllium window, and then we can collect the X-rays from both the sides. So X-rays are of two types. So one is the Bremsstrahlung X-ray, which is the electron which are passed from the near the nucleus. So its path is a little bit of deviated, but there is no energy loss in emission. However, in the characteristic X-ray, there is a the electron basically gets knocked out from its shell, and therefore there is a loss of energy from in that case. So the inner shell electron is removed, and an outer shell electron fills the vacancy. So that X-ray is what we call as characteristic X-ray, and this is very important when we want to determine what kind of material we are having. So every particular material or element is having a particular characteristic X-ray. So that's why it is called as characteristic, because the energy which is required for the removal of electron from the inner shell, and then after the electron is getting removed or knocked off from the shell, the other outer shell electron fills its vacancy, and it dissipates certain kind of energy, and that X-ray which we are trying to, like, that results in this interaction, that is the characteristic X-ray. And for a particular element it is different, so it is very specific for a particular element. That's why it is very important when we want to determine or characterize the type of material or the element which is present in our sample. So, how this X-ray radiation interact with the sample? So basically, any radiation, if we are bombarding it onto the sample, it can either get transmitted from the sample, or it can be scattered in a elastic way or an inelastic way. So, in elastic means the energy difference will be not be there. However, in the inelastic way, the energy will be difference will be there. So some of the energy will get lost. And maybe the sample absorbs some energy, or it gets reflected back or something like that. So in that case it is an inelastic scattering. So so when we are talking about the particular X-ray, so X-rays are when it is incident on sample, it can be either absorbed again, and it can either be transmitted. But particularly what we see in the X-ray diffraction is this characteristic X-ray and the Bremsstrahlung X-ray. So so these two are very important. However, this backscattered electron and outer electron, these are also important in some cases. So the backscattered means it is very close to the direction of the incident beam, and it is the radiation which is getting reflected back from the sample after elastic interaction. So there is no energy change as such, and so it is depending upon the atomic number. So from the backscattered electron beam, we can get an idea about the atomic number of the material of our sample. Then we have the secondary electron, which is the inelastic collision scattering of the beam, which ejects a weakly bound valence electron. So in this case, the inner shell electron, as I told, that will get ejected from or get knocked out from the shell of the electron, from its shell, because of the radiation of the X-ray. Then we have the auger electron, which is the electron which is an extra electron which is having extra energy. And so when the excited atom releases the extra energy to an outer electron, that is then emitted as an auger electron. So suppose if I will be able to draw, so this is the so this is the nucleus, and then we have another shell, and here is an electron, then one more shell, and here is one more electron. So suppose this electron got knocked out, and then this electron fills its space. So in that case, it will leave some amount of energy with it. So by absorbing that energy, another one more electron that will again uh, knock out. So that is the auger electron. That is the having the extra energy which is obtained from the transition of this electron from the outer shell to the inner shell. So then we have the X-ray, characteristic X-ray, and the Bremsstrahlung X-ray. So these are all electrons which we are getting because of the interaction with the electron beam. However, the X-rays will be only these two, Bremsstrahlung and the characteristic X-ray. So I told the difference between these two already, and then we have the unscattered electron that will get transmitted without interaction with the sample. So, and this will tell us about the density and thickness of the material or the sample. Then elastically scattered means a specific pattern gives information about atomic arrangement in space, and the inelastic scattered means the energy is lost, or Kakuchi band. This is another type of terminology used for enhanced scattering, which we will be talking about in the TEM, transmission electron microscopy technique. Okay. So, what is XRD? So, it is a non. So, XRD is basically X-ray diffraction analysis, which is a non-destructive technique. So, that provides a detailed information about the material based on its diffraction pattern. So, how the diffraction pattern is coming, that will give us the idea about the material which is present in our sample, and in what orientation or in what lattice is, what is the lattice spacing, etc. Those kind of information we will get from the XRD pattern. Then what is diffraction? So diffraction is nothing but the interference of bending of the waves. So suppose we have waves in a, so light travels in a straight line. You know that. So but when it is getting interference, or uh, because of the constructive interference, it will give us a shape like this when it is passed through a small slit, very small aperture. So that is what we call as bending of the light. So in this case, we are getting constructive interferences. So these are, imagine these as a full circles. So these are the constructive interference which we get because of the interference of two lights, two waves basically. So this, and then one more wave. So the maxima of one should be the maxima of other, and the maxima minima of one should be the minima of the other. So in that case, we will get the diffraction pattern, this kind of diffraction pattern, and that is called as a constructive interference. Uh, 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 or one more thing is there, so destructive interference. In that case, the minima will match with the maxima of the other. So in that case, it will be slightly shifted. The wave will be slightly shifted. So the minima of the first wave will be the maxima of the other wave. So that will coincide with that, and we'll get zero spectrum. Then, so what is the difference between the X-ray diffraction pattern and the radiography or tomography? So tomography relies on the fact that the X-rays are absorbed more strongly by some material than others. So, for example, bone or tumors absorb more muscle or fat. So more X-ray than muscle or fat. So in that case, we are able to see the contrast and see the bone and tumor present in the body. So because of the high contrast, because density is high in the case of bone and tumor. So that's how we are able to differentiate between the bone and the muscle. Basically. So therefore, the transmitted image which we are getting provides a direct image of the structure inside the body of or the object. So typically a length scale of millimeter or above is so that much uh, body image we can get from the X-ray tomography, and so this is a very valuable tool for the doctors. So X-ray tomography is also widely used in other fields such as material science and metallurgy. Also, so with the help of tomography, we can actually check the porosity of the sample of our sample or any material. And in contrast, the XRD produces a diffraction pattern. So here we won't be able to get an image as such. However, we will get a pattern. So it will look like this. So suppose this is the peaks we are getting in the X-ray. So this is a very rough diagram I'm sure. But this kind of peaks we will get in a XRD pattern. So does not superficially resemble the underlying structure and provides information about the internal structure or length scale. So it can give us the idea from about zero point 0.1 nanometers to 100 nanometers. So that range of structure we can characterize using the X. So what is the principle? So suppose you are following the X-rays on the sample, and the electrons are getting knocked out, and it will interact. The rays will interact with the sample, and then we will get a diffraction from the constructive interference. So this is basically uh, so this diffraction is gives us a idea about the distance between the atoms. So I'll be describing this more in detail. However, the diffraction basically gives us the idea of the distance between the two planes or two atoms. So as I told, the maximum of the first wave should match with the maximum of the other wave to get a constructive interference. So this intensity will get averaged, and this will get enhanced. So the peak will be very visible. However, if the maximum of one will be aligned with the minimum of the other, in that case we will get a destructive interference, and there will be no signal because the amplitude are cancelling each other. So that's why we are not getting any peak here. So then, elastic scattering is one where the, as I already told. So in this X-ray beam is directed on the crystal, and it interacts with the electrons of the atoms, and the emission can be again constructive or a destructive interference, as I already told. So it can be either from any of these electrons. So all will be if this is getting knocked out. So in that case, some other electron gets filled this space. So likewise, a lot of interaction will be there in a single sample. So first of all, for the crystalline material, basically it is very important to uh, know the periodic arrangement of the atoms. So even for the polymers, like how is the atoms are arranged in our material. So crystalline materials are characterized by the orderly periodic arrangement of atoms. So in that case, we can know the parallel planes of atoms which are intersecting the unit cell. So what is a unit cell? So this particular cube is a unit cell, and since all atoms are one atom is there at each vertex of the cube, so this is a normal simple cubic structure. I hope you know about the simple cubic and body cubic and face centered cubic structures. Are you aware of this, or should I explain it? You can answer me, like you need to. Okay, so it will be actually difficult for me to draw here, but I'll try. So suppose this is a cube, and it is having 8 vertices, so 8 atoms at each vertex, one atom at each vertex. So this is a simple cubic structure, SCC. In this case, what happens? These 8 atoms share their 1/8 of the part with the cube. So 1 into 8. So basically 1 into 1 by 8. So basically we have only one atom in this cell, because every atom at the edge, at the vertex, is sharing its 1/8 part with the cube. So this particular cube will be having only one atom as its share, because 8 atoms are I'm sorry, 8 atoms are sharing their 1/8 part with the cube. So the total number of atoms for this particular cube will be 1. So that is the case of a simple cubic structure. But so when we talk about the body cubic, in that case we have a extra atom present at the center of the cube. So this is the body cubic structure. So in that case, what will be the number of atoms? Total number of atoms? Can anybody tell me? Yeah, two. So one with the on the edges, so all sorry vertices, and one in the body center, so at the center, so that will be having a whole shear. So one cross one, that will be one for the body, like inside the center one, and then one 8 cross 1 by 8, that will be again one for the vertices. So 1 plus 1 2, total 2 atoms will be there. And in the face center, in the face center again, so we have on the vertices all 8 vertices, and 2 faces on the on 4 faces. 1 2 on all the faces, so 4 here and then 2 more, one at the front and one in the back. So 1 2 3 4 5 6, so 6, and all share their uh, half part in the cube, so 1 by 2. So 6 into 1 by 2, that will we will get 3. So here 3 and and on the vertices again, so 3 plus 1. So here we will get 4 atoms. So that is the difference between the symbol cubic, body cubic, and the face center. So I hope you understood now what is the difference between them. So this is the without the center one is the simple cubic. Then with the center one, that is called the body cubic, and on the faces, that is called face centered FCC. And the total number of atoms also, for the SCC it is 1, for the BCC it is 1 plus 1, it is 2, and for the FCC it is 3 plus 1, that is 4. Okay, so so coming to back to the XRD. So when the crystals are exposed to the X-ray beam, X-rays are scattered coherently by the regularly spaced atoms. So here we know what kind of what atom is present at which place. So these positions are fixed for a particular structure. Okay, so suppose we consider a simple cubic structure. So we know that these two planes are separate by a distance. Suppose this cube is having a dimension a, so these two planes are uh, so the distance between these two planes, this red one and the blue one, is a. So that we know from the basic crystal structure. So this will be producing a constructive interference, and then we'll get the difference between the two planes from the diffraction. So and that also we will get at a particular angle, not all angle will give us the peaks. So we need to scan it at through all the angles from considered from 10 degrees to 90 degrees. We will scan it through whole the range, and whole, like we need to actually rotate the sample to make the X-ray fall at a particular angle to get the peak out of it. So diffraction from different planes of atoms produces a diffraction pattern. So that peak we will get, and which contains information about the atomic arrangement within the crystal. So to get the idea about how where from where this XRD uh, actually innovated. So first is the crystal symmetry. So Nicholas Steno talked about the crystal symmetry, how the crystals, this BCC structure, FCC structure, how these are uh, formed in a particular material. Then Miller, Sir Miller told about the Miller indices, like to actually uh, what do we say, for the geometrical representation of these structures. So if we want to represent it in the form of a coordinate, so suppose this is the x and y axis. So this one is the 0 0 0 1. We have z axis also. So 0 0 0. Then here we will get 0. So suppose this is x. So this will be 1 0 0. For suppose this is y. So for this one it is 0 1 0. So like that, these are called the Miller indices. So this was proposed by Professor Miller. Then Rondon professor discovered the X-rays, and then Ewald formulated the ordered array of scattering and all. So then uh, Professor Max published the first diffraction pattern in the proceeding, and then these two actually this is a father and son duo that they actually studied the what is the basic principle behind it, and developed the Bragg's equation, which we know now as the principle of the XRD. So that is how the development of the XRD happened. So here, as I told, so this is a particular, suppose this is a simple cubic structure, and these are multiple structures like this, and these are separated. These planes are separated by a distance d. So from the here, we uh, we can actually calculate the distance d between the two planes. So here we know what lambda we are bombarding onto the sample, because the lambda is basically fixed for a X-ray machine, X-ray diffraction machine, and n should be an integer. So and theta we know was like we are actually rotating our sample, so theta will also rotate, and so from here we can get the value of d basically for our sample. So the interplanar spacing is what we will get from the from this equation uh, using the values which are getting from the XRD. So uh, so the angle between the incoming and outgoing beam are called as 2 theta, because here, as you can see, this is with geometry. It is basically 2 theta between the incident and the scattered ray. And in order for constructive interference, this has to be an integer number, this n. Then only we'll get a constructive interference. Then this is the Bragg's equation, which gives the relation between the lambda and the lattice spacing as well as the incident angle. Yeah. So there are different kind of structures. I only talked about the cubic structures. However, there are other rhombic structure also, hexagonal, trigonal, tetragonal. So these are all different kind of Brevis lattices. Actually, there are 14 Brevis lattices and 7 different crystal systems. So I talked about the cubic one where the sides are equal as usual. So A is equals to B is equals to C, as you can see in this one. And we have the primitive one. Primitive, that means the simple cubic structure which is having atoms only on the vertices, as you can see here. However, in the space centered or the body centered, there is a one at the middle also, and in the face centered one, we have one atom at the all the faces. So 6 atoms on the faces. So that was one structure which I explained to you. But however, there are other also. So triclinic. So this one is the triclinic, which is having angle also. So here we have angle alpha, beta, and gamma 90 degree. So suppose angle with the x-axis is the alpha, then angle with the y-axis, that is the beta, and angle with z-axis is the gamma. So here alpha, beta, gamma are not equal to each other and are not equal to 90 degree either. And here these for the cube we know that all the sides are equal and all the angle will be 90 degrees. So this is a basic structure. So from here, like we can uh, imagine the other structure also. So triclinic, which is having unequal sides and unequal angles of rotation. Then monoclinic, which is having alpha and gamma as 90 degree, however beta is not equal to 90 degree. And this is also having two structures, primitive and base centered. So here this is the simple one that is having atoms only on the vertices, and the base centered that means it is having atoms at the two bases, that means the top and the bottom base. Then we have orthorhombic. In this case, the alpha, beta, and gamma are equal to 90 degree, but the sides are not equal. So this is a orthorhombic structure. So again, this is a primitive one, that is atoms only on the centers, sorry, on the vertices. Then we have base centered, so atoms on the vertices as well as at the top and bottom face. Then the space centered, that means the it is having one at the body or the middle center of the lattice. Then we have the space center, that means atoms on all the faces. Then the hexagonal structure is also there, where like different uh, like the structure is having a hexagonal shape, and again here alpha sorry A and B, two sides will be equal and third side will not be equal, and uh, two angles are 90 degree and one angle is 120 degrees. So as you can see here, this is a single structure, and then we can combine it to make a hexagon. Then trigonal, so it is called as trigonal because the three sides are equal and the angle, two angles, all the angles will be equal but not 90 degrees. So that is the trigonal. Then we have tetragonal. So again, primitive tetragonal and space center. So tetragonal means the two sides are equal but third side is not equal, and all the angles will be 90 degrees. And again, the atoms are on the vertices, so it is primitive. And one is the space center, that is one atom at the body center, body of the lattice. So the information which we get from the XRD is it provides information on structures, phases, and the preferred crystal orientation and other structural parameters such as grain size, the salinity, strain, and the crystal defect also. So we will get information on the crystalline phases and lattice parameters. So lattice parameters are all these parameters. Suppose the sides of the cube or the angles. So this we can get from here from the XRD. Then degree of crystallinity. So whether the material is crystalline or not, that also we can check with the XRD. So if a material is crystalline, crystalline is all one of these crystal system basically, one or two, like combination of these. So in those cases, we will get a very sharp peak in the XRD. However, if a material is not crystalline, and that is if it is an amorphous, in that case we will get a broad peak. So in that way we can differentiate whether the material is having a crystalline structure or a amorphous structure. Then degree and nature of preferential orientation. So how the material is oriented, basically the grains are oriented. That information we can get from the example, and the texture of the design grain also we can get. Then grain size, if it is very coarse grain or very fine grain structure, those kind of information we can get. Then the density of dislocation. So dislocation or defects we can get from the we can get to know from the XRD. Then residual information about the residual stress or strain, that also we can get, and the film composition via the lattice parameter that we can get, and also the film thickness, if it is very thick or if it is less thick, or density also, that thing, those parameters also we can get. So coming to the instrumentation part, so first we have a X-ray source which incident on the sample. So with the help of a specific optics, we try to focus it on the sample, and this sample is attached with a goniometer. So this goniometer moves the platform, or it rotates in the x, y, and z direction. It can rotate in all three directions, and so with the help of that, then the X-rays are interacting with the sample, and that interacted X-ray we again try to detect it with the detector. So this is the angle 2 theta which we get in the curve also. So just a second. Yes. So then, so this why we call it as 2 theta. So okay, I'll try to draw it again. So this is what is called a particular X-ray, typical X-ray uh, peak or graph. So these are some of the peaks, and then here we get 2 theta, and here is the intensity. This is this is this the intensity I. So here we have intensity, and in the X we have 2 theta. So always we have to mention 2 theta here, not only not single theta, because the angle between the incident and the scattered ray is 2 theta, not a single theta. So that's why always we will see here 2 theta mentioned as the angle. So if these kind of sharp peaks are coming, that means our material is crystalline in nature. And if we are getting a broad hump like this, in that case, we know that the material is amorphous in nature. So first, so coming to the instrumentation again. First, we have X-ray source. So X-rays are produced as I told again, evacuated X-ray tubes containing a cathode, which is a tungsten filament, and a copper or molybdenum target metal anode. Then it is operated at very high voltage of about 60 kilovolt. And then we have the incident beam optics. In that we have a collimator to narrow the X-ray beam that consists of two sets of closely packed metal plates separated by a small gap. So here, this is uh, how it works. So we have a cathode, then electrons are falling onto it, and we have an anode, and this is the focal point. So the electrons fall over the target, basically, and this is in the presence of very high voltage. So this is about up to 60 kilovolt. Then we have a monochromator. So once the X-rays are generated, so with the collimator we try to make it in a narrow beam, and then with the monochromator we try to filter it at a single particular wavelength. So we have two kind of monochromator: filter monochromator and crystal monochromator. So in the filter monochromator, X-ray beam will be partially monochromatized. So filter absorbs the considerable radiation and passes the required radiation. And in the crystal monochromator, it is made of suitable crystalline material like NaCl, LiS, quartz, etc. So those crystals absorb the radiation and pass the required radiation. Then the goniometer, this is as I told, it is for rotating the sample at a particular angle. So the angle from the source and detector and the sample surface are set by goniometer. For typical powder pattern, data is collected from 2 theta at 2 theta from 5 degree to 70 degree. So why we take 2 theta, I told you. I explained the reason behind it. Then different geometries of goniometer. So we have theta theta goniometer. So the sample is fixed either horizontally or vertically, and the tube and the detector rotate in opposite direction. Then we have theta to theta goniometer. So X-ray tube is fixed and the vertically mounted sample are rotated, and omega angle is also rotated. And detector, so this is the omega. So this is the z axis, this is the phi axis, and this is the theta axis. So different then tilting angle volumeter. So at different angles we can, so again tilting in the psi or the azimuth angle theta, sorry, phi. So those kind of so there are a number of denotion of these kind of angles like tilting, what in what direction we are trying to. But basically we only take 2 theta normally, because that is the basic. That is how we do the basic characterization, and these are required in special cases only. So those are not required as such. Then we have attenuator. So attenuators reduces the intensity of the X-ray beam reaching the detector. So this comes in the form of a thin metal foil, which is placed in the beam path. So this is essential for detector, because if the intensity is very high, then the detector may become saturated and deviate from a linear response. So uh, suppose here, as we are following the incident X-ray on the sample. Uh, so most of the incident ray will try to scatter back, because not everything, not every wave will interact with the sample. But we want to check very small interaction with the sample. So in that case, we need to put an attenuator in it, so that we do not get a very high intensity because of the incident ray. Because we know that it is a very high voltage and very high intensity beam is falling on the sample. So if it is everything is getting scattered, in that case we are not able to get the signal basically, because most of it is getting scattered or reflected. So in that case we need to put an attenuator to get the desired signal out of it. So that is the part of the attenuator. Then the detector. So detector converts the incoming X-ray to an electrical signal, and the unit based is usually counts per second. So here is the intensity, that is in counts per second, and here in the x-axis we have 2 theta, that is in degrees. And also we need to for a particular X-ray instrument, XRD instrument, we have a particular wavelength for it. So that is specified by the instrument, like it is specified for a particular instrument. So this will vary instrument to instrument, but it will not vary much. But still, there is a certain value for a particular instrument. So that we need to consider when we are calculating our lattice spacing. Basically. So detectors are defined by their dimensionality and can be zero detector, line detector, or area detector. So 0D, 1D, or 2D. Then the working principle can also vary between different detectors, and common types of principles are proportional counters, scintillation counters, and solid state detectors. Then two primary optical modes. So we have Brentano PV optics. So it is also known as focusing or parafocusing optics, are typically used for powder X-ray diffractometry. The position of the source and sample surface and receiving slit form a focusing circle with a radius that depends on the theta angle. So here you can see this is a diffractometer circle. This is the receiving slit, and here this is the focusing circle. So that is how the BB optics work. So we have two circles, diffractometer circle and the focusing circle. The position of the source, sample surface, and receiving slit are on the focusing circle with a radius that depends on the theta. So the radius of this circle depends on the theta angle, and the sample surface is kept on the tangent plane by the focusing circle, defined by three spots at sample, X-ray, source, and the receiving slit. So three spots are there, and on the tangent one, the sample is kept. The incident and diffracted beam slits move on a circle that is centered on the sample. So this receiving slit and the diffracted, so the incident one and the diffracted one, both moves on a circle. So this will move on a circle, and and is center on the sample. So sample is at the center. Then divergent X-ray from the source hit the sample at different points, and during the diffraction process, the X-ray are refocused on the detector slit. So here we are getting a divergence slit. We have a divergence slit here, and here again it is getting converged. So we have a scattering slit which converges the signal or the rays, and on the receiving slit we will get a point, point kind of ray. So this geometry requires that the source to sample distance be constant and equal to the sample to detector distance. So source to sample and sample to detector distance should be equal. So that's why the sample should is to be kept at the center. Then we have parallel beam optics, the PB optics. So in this case, what happens that the PB optics provide a very accurate measurement of the diffracted X-ray position unaffected by the sample shape. So in this case, we do not need to worry about the sample shape basically. However, in this case, it has to be very flat and small to fit in the center, basically in the center of the circle. So here we do not need to worry about the sample shape. Then a capillary collimatic optic, that is the Gobel mirror. So here we have a Gobel mirror, is used to form an intense parallel X-ray. So here we are following the X-ray in a parallel way. So in the previous one, we are trying to diverge the X-rays and then again converging it back. However, in the parallel beam, we are following the sample. We are trying to fall the parallel X-ray beams on the sample, and then again very high X-ray intensities will again get reflected or diffracted from the sample, and then we will detect it on with the detector. So the parallel beam XRD is insensitive to errors and associated with sample displacement. So in this case, we do not need to move the sample. That's why we are not getting any errors in this. So it is insensitive to errors associated with sample displacement. It virtually eliminates all the other well-known instrument error functions which contribute to asymmetric peak broadening, such as non-flat or rough specimens, actual divergence, and sample transparency. As a result, minimal sample preparation is required. So in this case, sample preparation is not at all required. Then preparation of powdered specimen. So in the case of powdered specimen, we need to have a very smooth surface. So in an ideal powder sample should have many crystallinities in random orientation. So it will be crystalline, but the orientation will be very random. So it should be smooth and equally distributed. So the sample, which is kept, the powder sample should be very flattened, or it should be very smooth, and the crystallinity should be less than 10 in size in to get good powder statistic. Then large crystallite sizes and non-random crystallite orientation both lead to peak intensity variation. So if there will be the crystal sizes will be high, and in that case the peak intensity will vary a lot. Then we have grazing angle, incident angle diffraction. So this grazing angle means the angle less than 5 degrees. So it is at very small angle at less than 5 degrees. In that case, the X-ray is just focused on the topmost surface. So as you can see here, suppose here the angle is very less in this case. Here, if it is very less, that is 5 degrees. So the beam will fall like this. It will just touch the sample surface and then again reflect or scatter. So it will give the information on the topmost surface of the sample. And this grazing angle, incident angle diffraction can perform many of the analysis possible with X-ray, uh, with the added ability to resolve information as a function of depth profiling by collecting successive diffraction pattern with varying incident angle. So when we change the angle, the depth will increase. So that is how with at different angles we can get the information from the depth. So depth profiling we can do with using this grazing incident angle diffraction. So here is a qualitative analysis of the XRD data. You see there are some of the peaks. So at the position 2 theta of 64, 66 and 68 degrees. So if we, uh, so the bulk area is the blue one here, and the nanocrystalline area is the red one. So in the case of nanocrystalline material, we generally get a broad peak. However, in the bulk material which is crystalline, we get a very sharp peak, as you can see here. So this kind of things, phenomena happens in the XRD, like because in the nanocrystalline material, we do not get a very specific crystal information about the crystal lattice and all. So that's why we are getting a very broad hump. So the experimental XRD data are compared to the reference pattern here. So this is a reference pattern, the vertical lines, the red one. These are the standard data, and our data, that is the peak position. These are compared with the standard data. So if the peaks are coming at these points, that means the sample peak is matching with the data that is already available. That is the expert high score data. So this is basically JCPDS files which we have in the software itself, and those are standard files. So that if that peak matches with our peak, that means the the characterization is correct. That means the element is the same as the decibelius or the standard one. So that helps when we try to analyze our data, that what element are present. So the peak matching should be done using the expert high score software. These are the software for the XRD, expert high score and match. So using these softwares, we try to match the peaks with the standard data for our sample. Then specimen displacement error will cause a small amount of error in peak position. So if there is some error in the displacement of the sample, then it will cause a error in the peak position also. As you can see, like if there is a little bit of error, like 60, if suppose only 1 degree error is there, then this peak will come at 65. Then the peak will not match with the standard data. So in that case, the our data will be not be considered, or it will be having errors. Then, so XRD diffraction pattern is the sum of the diffraction pattern produced by each phase in a mixture. So here we will get all the phases. So suppose we are having two phases of the material, and like two crystal lattices. One is FCC and one is BCC. So both of those crystal lattices, the information of those will be there in the XRD. So a different the peak position, different peaks will be there, and there will be both BCC structure and FCC structure. So in those cases, we'll get a combined XRD plot. Then so here the diffraction peak broadening will also occur. And it contains the information about the sample microstructure, as I told. So peak broadening may indicate smaller crystallite size in nanocrystalline materials, or more stacking faults, or microstrain and other defects in the crystal structure, and an inhomogeneous composition in a solid solution or alloy. In those cases, we still get a peak broadening. Then, however, different instrument configuration can change the peak width too. So, if the instrument is different, then the peak width will also change in those cases. Then the phase identification. So, as I told that different structures will be having different phases. So, the Miller indices that I talked about. So, these are the Miller indices here mentioned here. So, for the cubic, we have A equals to B equals to C, and so this is a cubic structure A1, and then the second one, that is B, is the tetragonal. So here A is equals to B but not equal to C. So the third height is different, and A and D are same. Then we have orthorhombic. So in this case, all are unequal. All sides are unequal. So these will having a different uh, Miller indices. So those that kind of information you can get from the XRD, and the planes we can match with the peaks. So this peak will be indicating certain planes in the crystal lattice. So that we need to find out that which plane is corresponding to which peak, or which peak is corresponding to which plane. So that information we can get from the standard JCPDS data, and we try to match it with our sample, and then we try to calculate that what will be the like identify what will be the structure of our sample. Then the peak broadening, as I told. So if the peak is broadening, that means there is a strain in the sample. So as you can see, it should be straight, but it is distorted because of that we are getting a broad peak. So it is non-uniform strain, and so here we are not getting constant peak broadening. So it is randomly broadened. However, if it is a uniform strain, so suppose it is elongated in a particular direction. So in that case, it is a uniform strain, so it is shifted. So peak will not distort, like it will not broaden, but it will shift a little bit. So non-uniform strain and peak moves, no shape changes. So here there is no shape change in the uniform strain. And then we can do the quantitative analysis of also of the data. So with the help of this Bragg's law or Bragg's equation, that is uh, lambda is equals to d sine theta, or n lambda is equals to d sine 2d sine theta. That information of the lattice spacing, as I told, you can get from this equation. We know the lambda and we know the theta also. So at a particular angle, what is the lattice spacing that we can get using this formula. And so this is the Miller indices. So this value we will get uh, is what is the Miller indices. It is represented as HKL, or the diffraction peaks from the published reference pattern. So this we need to again match with the standard data. So using this equation, we can calculate different lattice spacing for different lattice parameters. And most analysis programs contain an unit cell refinement algorithm for numerically solving the lattice parameter. So this you do not need to manually solve it, but in the software itself they have it as a built-in algorithm to numerically, like, to basically calculate this kind of equations. Then the crystallite size. So again, using this formula, we can get the crystallite size. So polymer crystals are on the order of hundreds of angstroms, and broadening of the diffraction line can be used to measure the thickness of the laminar structure crystals using the Scherer equation. So this is the Scherer equation. So size equals to zero point 0.9 lambda by b cos theta. The lambda we know, zero point 0.9 multiplied by lambda divided by b cos theta, and here B is the peak width. So peak width is what, where we will consider the peak width. It will be the full length half maximum, full height half maximum. So it's FWHM, full width half maximum. So that means if it is, the intensity is 100, then at the half of it, that is 50, intensity at 50, we'll we will calculate the width of the peak. So that is the width, that is B, which we will put here, and the cos theta, theta is the angle that the maximum intensity is coming, and this is the half reflection angle. So if it is coming 60 here, then we will take 30 degree here. Then degree of prosperity also can be calculated using this formula, where so xc equals to ic by ic plus ia. Ic and ia are the integral intensity of the crystalline and amorphous fraction. So suppose we have a peak like this, so it is also broadened and crystalline at the same time. So it is having some kind of amorphous nature and some kind of crystalline nature. So in those cases, uh, we calculate the degree of crystallinity using this formula. Then, so different applications are there, as I already told. So these includes measurement of sample purity, determination of unit cell dimensions, alpha, beta, and gamma, and ABC sites. Then the characterization of crystalline materials and determine structural properties including lattice parameters, grain size, strain, epitaxy, phase composition, and preferred orientation also. Then we can characterize the thin film samples also and measure the thickness of thin film and multi-layers, and then determine atomic arrangements in the sample, and identification of fine grained minerals such as clays, mixed layer clays that are difficult to determine optically. And then we can determine the model amount of mineral also in a sample. So this is a example of a polymer XRD pattern. Polymer patterns are additive. So here we see the first peak is the polyisobutane, then we have polyethylene. So when we combine these two in a ratio of 68% polyethylene and 32% polyisobutane, we'll get the peak of both of these. So it is a addition. So these peaks are additive. Like, we'll get combined peak here. So here we are getting some kind of broadening and then some kind of crystallinity. So both amorphous and crystalline natures are shown here. So this is to used to distinguish the block copolymers or alternating or random copolymers. Those kind of difference we can observe from the XRD. Yeah. So as I told, so polyethylene is highly crystalline, so it is giving us a very sharp peak. Then polypropylene, it is semi-crystalline, so we are getting sharp peaks, but still there are some humps also. And then cellulose, so it is microcrystalline, so it is giving us like this. So because of microcrystallinity, some the peaks are getting broadened basically. And for the polycarbonate, that is amorphous in nature, so we are getting a very broad peak like this. So this different kind of structure will give us different crystalline properties. So different XRD peaks also. So suppose this is the solution, then we are getting amorphous phase, then it is becoming crystalline, and then oriented crystalline. So it is random crystalline, and then it is this oriented. Then we can determine the thin film growth also. So at different intervals or different treating time, we can observe the changes in the peak intensity, and if new peaks are coming or old peaks are diminishing, those kind of changes we can compare, and then check whether what kind of structure is forming with the treatment. So the first one is the as deposited one of the chromium. Then we are heating it at 200 degrees Celsius to oxidize it. So then we are getting chromium oxide. Then again heating at 300, and again same thing is coming. And then at 400 new peaks are coming. So it is giving us two kind of structures, CR3O and CR2O3. And then at 500 degrees Celsius we are getting Cr2O3 majorly. So those peaks are very much prominent. And then again at 600 the same Cr2O3 is forming, but the intensity is getting increased. So this is how we can compare the growth of the material. Basically this is it for the thin film. Then for nanoparticles and polymer nanocomposites. So here the catch is that in the suppose we have a ZNO nanoparticle, so it will give a very sharp or highly crystalline peak. So these peaks are coming at these different two theta values, and the planes are corresponding to these are mentioned here. And the appearance of these peaks in the nanocomposite indicates that there was no change in the crystalline structure of ZNO when it was incorporated into the polymer matrix. So here, if we incorporate, so this was incorporated in the polymer, and still those peaks were coming. So this is the case of a ZNO nanoparticle incorporated in a polymer. And here we have a case of we have a clay which was modified using molecules of different alkylamine ammonium chain lengths, including these different chains and a modifier also. So this so first one is the C20, that is the modifier. Then we have C18, that is octadecyl amine. Then we have C16, that is hexadecyl amine, and the C12, that is dodecyl amine. So these are the XRD studies reveal that the T-spacing of the clay increases with an increase in the chain length. So as you can see, this shifts is there. So uh, as we see with the different chain lengths, we are getting a peak shift. So octadecyl means it is having most of the high chain length. Then we are getting a peak here. Then again it is increasing, and so the D spacing is increasing because of the peak shift we are getting. We are able to detect that. Then low density polyethylene, LDP, and organically modified OMT nanocomposite. So in the case of nanocomposite also, we can observe the changes in the position. And so in the X-ray diffractome of the OMT, we will intense peak at 001 at 2 theta 53.4, or it is 5. Okay, I'm not sure about this. So which is the characteristic peak of MMT modified with the alkyl group, and it is giving a D spacing of 25.8 Armstrong. So this sample was varied with composition. So they varied the composition of LDP, OMMT, and the compatibilizer, that is PEG, that is malic. anhydride, grafted, P, polyethylene. And these are prepared and analyzed by XRD. So with different ratios, the peaks are different. Then the XPS. So XPS is the X-ray photoelectron spectroscopy, and it is also known as electron spectroscopy for chemical analysis, that is ESC, and is used to determine quantitative and elemental position. So in the XRD, we are not able to get the elemental composition of the material. However, in the XPS, we can quantify the elemental composition also, and then the chemical formula and chemical or electronic state of the element, contamination or uniformity of elemental composition, etc. from the top surface. So ESC, that is XPS, is basically done on the characterize the top surface of the sample, but it can also be used to, in some cases, using a beam ion etching to get the depth profiling also. But normally we get the top surface information. Then a sample is irradiated with a monochromatic X-ray and resulting in the emission of photoelectrons whose energies are characteristic of the elements within the sample volume. So an XPS spectra is created by plotting the number of electrons versus their binding energies. So here we have a binding energy at the x-axis and the photoelectron intensity at the y-axis. So again, the idea is same. The X-ray knocks out one of the electron, and the electron when goes out, one atom from the outer shell falls down to the inner shell, and the energy which is radiated because of this uh, because of this transition, that is detected from the detector using the detector, and then we are able to get the peaks. So the basic principle is at different levels, like K, L, L1, L2, 3 again. So these are different energy levels or the shells, and the when the electron knock out from one of the sample, that energy we are getting, we are trying to detect. So the absorption of incident X-ray results in the ejection of core electron. The core electron that will get ejected, and this is an elastic process. That is, photons completely transfer their energy to electrons. When the electrons leave the sample without interacting with anything else, then it reaches the spectrometer. The kinetic energy of the ejected electrons is measured by the detector, and then each atom has a unique X-ray spectra. So as I told, to characterize the element, basically the characteristic X-ray here, that will be very different for a different material. So that will be very particular, basically. And this is a unique spectrum. So X-ray is a XPS is an elemental analysis technique that is unique in providing chemical state information of the detected elements, such as distinguishing between the sulfate and sulfide forms of the element sulfur. So suppose we want to check whether sulfur is present in a sulfate form or sulfide form, that can be distinguished using the XPS. Then X-ray penetrates the sample to a depth on the order of a micrometer. Useful electron signal is obtained only from a depth of around 10 to 100 angstrom from the surface. The X-ray source produces photons with certain energies, and we are having that. For example, for magnesium K alpha, photon with an energy of 1253.6 electron volt will be there. Then, if we are having an aluminium sample, then aluminium K alpha will be 1486.6. So if we are getting our energy in this range, then we know that if it is in coming around 1250, that means it is magnesium. If it is coming around 1486, then we can call it as aluminium. So those kind of characterization we can do. So the basic principle is the core electron with suppose with an with a kinetic energy Ek, it is are ejected by incident X-ray. So here H nu is the incident one. It is falling on the sample. It is ejecting the sample, the electron, and so that is having a kinetic energy of Ek and the binding energy of Ev, and H is the Planck constant, nu is the frequency of X-ray, and phi Sp is the spectrometer work function. So using this formula, we can calculate the kinetic energy of the photoelectron. So Ek of photoelectron decreases as the binding energy decreases. increases. Sorry, EK increases. The kinetic energy increases as the binding energy decreases. And a range of kinetic energy can be produced if valence band is broad. So depending upon the material also. So valence band, if it is broad, then in that case the very wide range of kinetic energy can be produced. And if the h nu is very less than the spectrometer function, then there will be no photo emission. And if the binding energy plus the spectrometer function is more than the h nu, then also there will be no photo emission. Then why do we check the core electron? So an electron near the Fermi level is far from the nucleus, moving in different direction all over the place. So it will not carry much information about any single atom. Suppose we have a core level here, and this is the valence band, and here we need to jump to this shell. So suppose the core electron will be having a very much information, because the other one that is containing very much high amount of information in that sorry at the higher level, that electron will not contain very much information, but the electron which is binded with the nucleus at the core, so this will be having very high information. It will carry more information as compared to the outer shell one. That's why we consider the core electron first. Then the Fermi level is the highest level energy level occupied by an electron in a neutral solid at absolute zero temperature, and the electron binding energy is the as calculated with respect to the Fermi level. So Fermi level, we know that this is the Fermi level where we need to jump the electron. The core electrons are local, close to the nuclei. So here, as you can see, the core electrons are closer to the nucleus and have binding energies characteristic to their particular element. So that's why we always consider the core electron, because those are having binding energies which are characteristic to that particular element. And the core electron will have a higher probability of matching the energies of aluminum K alpha and magnesium K alpha. Then photo emission process. So this can be thought as three steps. So first one is the photo absorption and ionization. So initial state effect. Then we have response of atom and creation of photoelectron. That is final state effect. Then there is a transport of electron to surface. That is the intrinsic effect. So we have a initial state where the photon is getting absorbed and ionized. Then the atom creation of a photoelectron. So we will get a photoelectron at the final state. And in between we have a transport of electron to surface. That is the intrinsic effect. So these are the notations basically for different elements. We have these notations, different notations for those, and it depends upon the spin number and the principal quantum number basically, and the spin quantum number, and also the total angular momentum also. So these needs to be considered when we are talking about the experience notation. Then we have the inelastic mean free path, that is lambda INFP. So this is a universal curve for the INFP. So when an electron with kinetic energy E moves through a solid matrix M, it has a probability of traveling a certain distance before losing all or part of its energy due to an inelastic collision. So as I told, in inelastic collision, the atom will or the electron will lose its energy upon traveling. So that is the inelastic collision, and because of that, we will not be able to detect the signal basically. So the average distance traveled before a collision is known as the inelastic mean free path. So we consider the average distance which is traveled before collision. So to get the inelastic mean free path, so how much uh, to check how much mean free path we will be able to get to so that range we can actually calculate to from the average distance which is traveled before the collision. And if a photoelectron loses the kinetic energy in a collision, it will contribute to the background rather than a characteristic no loss peak in the spectrum. So if it is loses the kinetic energy, that means it will not move. So the photoelectron will not move, and it will contribute to the background. So rather than a characteristic, so it will not give us the information as such. but it will rather be a background signal. So therefore, the X-rays technique is very surface specific. So it's the beam will not go in very depth of the sample, but it is more of a surface specific technique. So this is some of the formulas which are associated with this uh, with the enlarged horizon. Then we have different binding energies. So as we know, the inner shells which are very close to the nucleus, these will be having very high binding energies. So binding energy of 1s will be obviously higher than the 2s and the 2p and then the 3s. So as we know that these lies like this, and the atomic number, with the atomic number it will vary. So for the atomic number, if it is less, then we check the 1s. Then if it is increasing, then from 1s to we check the 2s, then 2p, then 3p. But the binding energy will be higher for 1s. Then the binding energy of orbital increases with Z also. Z, that is the atomic number. So binding energy of the sodium is higher. Lesser than the binding energy of magnesium. That is even lesser than the binding energy of the aluminum. So depending upon the atomic number, if it is higher, then the binding energy will also be changing. Then I'm skipping this part. This is the instrumentation. Basically, we have a source and an electron energy analyzer and a detector, this is a detector, and a two-way system, a very ultra high vacuum system basically. So this is done on in a very high vacuum. So the X-rays are falling. So from the X-ray source, we try to filter uh, the irrelevant part and only keep the X-ray which we want of a particular wavelength obviously, and it will fall on the sample and the photoelectron will be knocked out, and then it is detected with the detector. So this is focused with a lens, and so many things are there. Splits and also are there, and it is all enclosed in a very high, ultra high vacuum conditions, and then we acquire the data yes, in the form of like this. So this I'll go to the question answer first because I'm not having much time. So, uh, if the atomic number of the zirconium, molybdenum, palladium, and tin are 40, 42, 46, and 50 respectively, the suitable filter for X-ray radiation from molybdenum should be. So, can anyone tell me what should be the answer for this? Hello. Any guesses? Hello. So here the least atomic number is the 40. So that's why we will use zirconium as a suitable filter for the XRD from the molybdenum cells, because there is a difference between these two. The distance is very less basically, but still that is a suitable filter for the XRD radiation. So the next one is the relationship between the minimum wavelength of X-ray radiation generated from a target metal and applied voltage is given by which of the following equation. So can anybody tell me what should be the answer for this? Hello. Can anybody answer this question? Hello. Yeah. So basically, what the question is, anybody willing to answer? Uh, I'm afraid because they are asking the relation between the minimum wavelength of X-ray radiation related to the generated from a target metal and applied voltage. So wavelength and voltage both should come in the equation. So can anyone guess from this all four options? Yes, D. Exactly. Yeah, exactly. So this is the lambda minimum, that is the minimum wavelength of X-ray radiation generated from with the applied voltage. So this equation is containing both lambda and the voltage. So that's why the Van Hunt equation will give the relation between the wavelength for the X-ray radiation generated from the applied voltage. So option D is correct. Then the third one is it possible to determine protein structure with X-ray diffraction? Because the diffracted X-ray can be used to directly obtain an image of the molecule on film. The diffracted X-ray can be refocused to give an image of the object, just like a microscope. Interference between the diffracted X-ray depends on the relative position of the atoms or all of the above. Can anyone answer? So, does the X-ray XRD gives us the image of a molecule? Is it a correct statement? No, right? So it will not give us the image of the molecule. Then the diffracted X-ray can be refocused to give an image of the object, just like a microscope. So it will not work as a microscope also, right? It will not give us the image exactly. Right? Yeah. Then we have the interference between the diffracted X-ray depends on the relative position of the atom. Yeah. So we will get a interference, a constructive interference information basically, and those interference diffracted ray will give us the idea of the relative position of the atoms. So as I told, the lattice spacing between the two planes, that information we will get from the constructive interference. So that's why option C is the correct one, and A and B are wrong. So D is also wrong, and so option C is the correct one. Then during destructive interference, the path difference between two waves should be. So anybody tell me which one should be there? Which one? Path difference should be how much? No, that n lambda should be for the constructive interference, not for the destructive one. I told you that the n value should be an integer if if we want to get a constructive interference. In that case, the n should be an integer. But for destructive interference, which one should be there? Which one of these? So in the destructive interference, we will not get any peak. We will not get any intensity in that case. Sorry. First option is again having a multiply multiplied by 2, right? So it will not be the correct answer, I guess. Yes. So sorry. I think this question is somewhat confusing. I think it should be constructive interference. I'll check it again. So this answer is, I think it is wrong, but still I'll check. Then the last question is the statement one. Uh, it tells XPS is a good technique for measuring the atomic concentration of a bulk sample. So is it correct? Or statement 2 also tells when an electron from a higher energy level fills the hole left by an ejected core electron, resulting in the emission of an agar electron. So which one should be correct, or both are correct? Can you tell me? Yeah, exactly. Statement 2 is correct. That means when the high energy X-ray falls on the sample, the electron from the higher energy level fills the hole left from the ejected core electron. So core level electron will get ejected, and the higher energy electron will fill the space, which will result in an emission of an other electron. So statement 2 is the correct one. And so XPS is not for a bulk sample, as I already told. It is normally used for surface analysis. So that's why statement 1 is wrong and 2 is correct. So answer is B. So with this, I finished with the questions. You can ask your doubt if you have any doubts. Sorry, sorry, hello. I could not hear your question. Yes, 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 yes. Yes. Where was it? Like, I am not sure what you're talking. Assignment question. I I will check. I am also not sure what is UPS here. I only know XPS. I am not sure what you're talking about. So I'll check that, and in the next task maybe I will try to explain that. Because in this one only XPS is there. Still I'll check. Everyone is excluded. Okay, I will check that. In the next class, I will try to check. Okay, okay. So in the class, in the lectures, did you get an idea about this? Okay. No? Okay. Okay, then I will check that. Okay, in the next class, I will try to explain it. Okay. Any other questions? So you can leave them.